Welcome everybody again to one of our MakerBot professional webinars. I'm joined today by Michael Tapas here, one of our leading engineers here on the MakerBot team. My name is Cañada. And today we're going to be talking a little bit more about the method and how, basically, what it means to have it around you, some of the benchmarks that we've been trying to create in order to test the machine, to take it to the limits. I don't know if you want to speak a little bit about your your part in developing method and
Yeah, so I've been at MakerBot for many years now, between 5 and 6 years, and kind of been here from the beginning of method. And so with method, we were kind of looking for improved part tolerance, part quality, reliability. We didn't really see anything like that on the market, and so that's when we kind of started developing method and kind of picked the things that we know we needed for that. So increased rigid frame, a heated chamber, dual extrusion to have dissolvable material like PVA, and kind of started from there.
Cool. Well, just kind of to describe the setup that we have here, we'll be running between the camera, some of the proof points that we have, a deck that we prepared for you guys, and then also some shots of the printer. I don't know if we can bring it now into view. The printer will be kind of... Get rolling with some of these tests that we've been conducting with the printer. So as I was saying, right, we've talked at length about what MakerBot is, what method is, and we've heard a lot of people asking, well, what does it mean to be a performance printer? What do we mean by that? And I think that in a way the quick takeaway is that we're trying to mix the best of two big worlds, right? The desktop printers and the industrial printers. We're trying to find a sweet spot between the two of them. And if we go to the next slide over, we know that desktop printers are really good at being accessible, being easy to use, but they struggle when it comes down to precision, to part tolerance, accuracy, and that's actually where industrial systems tend to shine, right? They are really good at being precise, really good at being accurate, but, well, they're not as easy to use. More often than not, they're going to be gated by a technician, as opposed to being, or a regular user in an office space, in a manufacturing space, being able to have open access to it. And that's where we started with method. And after having developed it, we wanted to create a series of tests for it in order to see if it was actually delivering and living up to what we wanted it to do, right? Kind of like what your job was when developing the printer and making sure now that it's actually playing good, or making sure that it's delivering on the promises that we've made. And that's where we developed, or how we started to develop this benchmarks test. So just as a reference, those parts, and if we go to the next slide over, those parts are already in Thingiverse. You can find them all. Here's the part number, or actually the thing number. It's 3423013. You're more than welcome to download the STLs and print them on your own. There's 3 parts. It's what we call the feed cube, the hub, and the gripper. And we're trying to test with them 3 different things, right? With the feed cube, it's about precision. It's about printing with tight tolerances. With the hub, it's about cylindricity, which means, I don't know if you want to talk about a little bit of what we mean usually when we talk about cylindricity, and what does that mean for a part to be accurate.
Yeah, so with 3D printing or FDM printing, you have a gantry that's moving around in a circle oftentimes. And so if a machine isn't rigid enough and not precise enough in its movements, you really won't get a perfect circle or something close to a perfect circle, and you get more of an oval. And so if you have a 10 millimeter diameter, that size may fluctuate between 10.2 and 9.8. Mm-hmm. And so when you go to fit your part in there, it'll actually be undersized for what you need. Right. And so on the method, we have the dimensional stability to be able to make a nice circle.
Yeah, so that's an interesting challenge when you're trying to play with both axes at once, as opposed to just calling out a single one. And then another important thing to set up straight from the beginning, because we've had a lot of questions around it, and if we go to the next slide over, are the engineering tolerances, right? So we were being asked, at some point somebody brought up that they couldn't find any tolerances in our parts. I think, we're testing three main types of tolerances. The first one being what we call, or what you would call, a close running fit. That basically means a part that's it's not entirely loose, but it tries to slide, between the components. That's where our gripper part, the one on the left, is trying to show off. So it's a printing place assembly. Fairly complex overhangs, a lot of different moving parts, little rods and spindles, and they all need to move freely. The second type of tolerance is a press fit, right? Something that's going to be have a tight lid between the two parts, and it's kind of, you have to exert some force on the part in order for it to close or to match the next part over. And the third one will be a similar fit, which is borderline and interference fit. That's what we are using our hub for. The reason being, in that case, is that you're trying to house a bearing. In this case, you can see it in the image there, a machine bearing that needs to, be tightly fit up against that part. And overall, we're talking about anywhere from 0 to 100 microns tolerance between the parts. I don't know, generally speaking, what's the types of tolerances that you see when asking, for a machine shop to do either an aluminum part, a cast part, or an injection molded part?
For most of the injection molded parts, depending on how they're mating and how they're fitting together, you're sitting anywhere between 100 microns and 250 microns on small components. On larger components, that changes just because the part has more shrinkage and possibly warp, and so that might increase to plus or minus 0.5 millimeters or something of the sort. But generally, small parts that fit in your hand were maybe like 100 micron range to 250 micron range.
Right. And then, what would you say, from, I guess it's a kind of a naive question in a way, but what's the importance on keeping the tolerances or having tolerances in your parts? What do we mean by them, and what do you use them for?
Right. So when you go to production, we're going to be shooting thousands of parts, and we always want to make sure our parts fit together, whether you shoot a part in January that it gets made, or you make a part in December, the following 12 months, that they fit together and that you don't get interferences. And generally, if two parts are mating together, you want something maybe a little bit tighter. If there's not a lot of criticality that they mesh together, you put maybe a little bit of bigger tolerances just to give yourself some breathing room.
Yep.
Or it might be a press fit for a pin. That's a very tight size, and you hold a tight tolerance on that.
Right. So, well, I guess, that's kind of, let us know if you had any questions. Actually, I forgot to introduce the rest of the team over here. We have Allison and Anastasia answering questions, and actually on the production side, and Yael shooting over there with behind the camera. But if you have any questions as we go, feel free to ask them, and we'll try to address them as we keep going. So now that we established what we mean by tolerances, let's start with the first set of tests, right? And the one thing that we're trying to do is we're trying to connect individual tests to specific features of the printer, right? In this case, starting with the ultra rigid metal frame, and we've talked about it on the last webinar. What that means is basically having a machine that knows or that you can trust in regards of having the ability of moving precisely in all of the axes, not wobbling as much. And we'll talk a little bit on what that means. Specifically, if we go to the next slide over, on this first test about, and you'll see it in kind of the diagram coming up. What we created is, if you can hand me one of those blocks, yeah. So we created this very simple part, right? It's a straightforward one. It's basically two blocks that fit together. However, the tolerances, as Michael was describing, they're fairly tight, especially for an FDM machine. We weren't sure if it was actually going to, if it was actually going to be living up to the test, Yeah, because we did only a 50 micron offset tolerance, and that's pretty tight, right? Especially for an FDM machine. But the cool thing about it is that it actually, once you align the part correctly, it slides in place. And I don't know if we're getting this in the camera, but we'll see in the next slide over some of the reasons why, in this case, it does slide. And we also have another sample here. I'll bring it over, a desktop competitor sample, which also claims to have similar part accuracy, but it's just once you try to line it up, it won't line up, and you'll see that in the next slide, like showing kind of like that, um, yeah, really close up view of the part. So you can see how I'm calling out that bulging corner in the slide. And the reason why, well, actually, I would like to know what's the reason behind that. When you're comparing the two parts, the competitor and the method one,
Mhm.
we see one has very sharp corners, and the other one, it's hard to tell it, with the naked eye, but there's something going on in the corners.
Right. So with the method, there's kind of two things happening in the print. And if we start with the bulging corners, you can see that it actually makes the part bigger. And so with the extrusion process, as we come into the corner and slow down and speed back up coming out of the corner, we try to control our filament process coming out of the nozzle very well. And that allows us to keep a correct bead width,
Right.
so that what we've modeled and what comes out in the part are as expected. And the second thing would be the rigidity of the frame, which is really the kind of like a resonance or noise you see on the surface of the print. And as the nozzle comes around the corner, it'll actually wobble some.
Yeah.
And so trying to reduce that as much as possible.
And how is it like? Because if we were to, kind of diagramming out what you're having here in the sharp corner, you really want. You're describing. It's basically like using this very fat marker, right?
Right.
So you're trying to do what you're calling. You said you called out the bead width. What do you mean by that specifically?
So our nozzle width is 0.4 millimeters,
Uh-huh.
and that's what we expect our bead width to be
Okay.
at all times. But as you accelerate in and out of the corner, you can get a bead width that looks a little bit more like this. And so
Mhm.
it comes out fatter, and will actually make a radius here and bulge on the outside.
Right.
And so now your part tolerance has changed just for that feature in the
Right.
corner.
So you might be able to have very good straight lines, but once you're trying to change direction, then
Right. The
Okay.
acceleration and deceleration
Mhm.
becomes very hard. And also you'll get like a noise with the kind of nozzle wobbling
Mhm.
across that surface. And eventually it dies out,
right.
but you'll see a ringing on the edge.
Okay. And then, so coming back to the part itself, and you have like, so that you see in higher resolution, I guess. If you go back to the slides, you see that GIF of, it's actually me testing out the two parts. In one hand, the method part, and the other one, the desktop printed part. And it is kind of tricky, right? So it is kind of tricky to see or actually to fit it because of these reasons, right? It's kind of, you might have the ability to run a straight line smoothly, but as soon as you're trying to change directions, and I guess you're doing that quite a few times in a printed part,
Right.
then it gets challenging.
Absolutely.
Yep.
What printer are you guys comparing to, or at least what's the price range?
Oh, okay, the price range. That's good. So we we got asked on it before on the last webinar. We don't want to disclose any specific names just because it would be not polite, I would say. But the price range, they are running at about $300 to $6,500. Some of them are a little bit more expensive because we're also using industrial grade printers. Because again, we are trying to match the quality delivered by industrial systems. You guys know that our parent company Stratasys has a few of them. They start at $20,000 or more. We have a Uprint upstairs. We have one of the Forduses, I think. And yeah, that's the ones that I can call out because we work with them. But the rest of them on the desktop systems, they are over $3,000. So we know that there's printers that are way cheaper. But also there's two things, right? They don't have the features that we're trying to compare them to, so it would be unfair to try to compete with them. And at the same time, they require a lot of tinkering around with the machine. So as a ballpark, it's printers that are over $3,000, mainly in kind of like that high end of the spectrum of the desktop printers. I hope that answers the question. So moving on into the slides, right? We have that next slide over, showing a little bit of what you were calling out, that resonance, right? We have on the right we have the desktop competitor, and on the left we have the method, and you can see how the bead length, the bead is actually super smooth on the method, and there's waves there. Like how, where do they come from usually?
It comes from the machine vibrating.
Mm-hmm.
And so if if parts don't fit together well or things aren't secure,
Yeah.
you get a vibration that happens, and so it comes from the rigid frame and then transfers to the nozzle. If the bill plate is moving a little bit and vibrating, it'll show up in the print.
Okay.
So it's kind of a top to bottom system system problem.
And then what do you usually see like with desktop systems, specifically what components of the system what were you trying to solve, I guess, because we have our Rep Plus as a desktop system, right?
Right.
Specifically, which are the components that tend to give you those results, that kind of waviness in the part?
Good question. It's probably different on every machine. For the method, we wanted to really beef up our extruder and carriage, increase the stiffness there. That was kind of one of the negatives on the Rep Plus that we knew we could gain a lot of print quality from. And the second is the rigidity of the frame more than anything else. Really allows for that, and the gantry not kind of twisting and warping as you're accelerating and decelerating.
Especially because more often than not, you'll see these printers that have basically either plastic or maybe in some cases aluminum sides, but they are not like a single component, but rather just like leads, right?
Right.
Trying to fit together, and then the rod. So every single component that's being tied into one another.
Every component, the bearing, how you mount the shaft to the frame, every little component will account for some amount of either stiffness or play.
Cool. Well, and then next one over, again, reiterating that same test. This is a different one, just kind of a more organic shape, but you can see that it's also happening there, where you see a little bit of that waviness on the left with the desktop printer, and a much smoother surface finish on the method, right? It's like kind of like, it doesn't always have to do with just having, not only in straight lines will you see that waviness, I guess that's what I'm trying to say. But yeah, and moving on kind of to the next tier of features and the next tier of challenges, we have our dry sealed material base on the first hand. So basically with method, instead of having the filament exposed to the environment, you actually have it in an enclosed drawer that keeps the humidity levels at bay, and we'll talk a little bit about what that means. And the second feature is, the ability to use PVA. We know that that's not something new. There's a lot of printers out there that use PVA. However, there's different ways of managing PVA, and PVA is a sensitive material. I don't know if you can tell us a little bit more about what PVA is in a nutshell, and why is it important to be careful with it.
So we use PVA as our support material, and it's water dissolvable.
We have a few prints out here with PVA, if you want to. Yeah.
And so these are goggle model, and we have the model material here is our tough material, and the kind of translucent material is the PVA, and so it's water soluble. And so what that kind of allows you to do is not to have model material support that you don't have to break off. So it kind of gives you some more design freedom on how you orient your part, and not really have to think about the breakaway material or designing for the part to be 3D printed. And what's really nice is, since it is water soluble, you can put it in a bath of water and it's non-toxic, which is what's so great about it. But also makes it so difficult because there's moisture in the air at all times, or in varying amounts. And if you leave PVA exposed to the air, it will naturally start to break down.
Yeah.
And so that's why we needed to have a sealed system in the drawer, so we always maintain our material quality.
And we were talking about it yesterday. That you were showing me this slide over here, the next one over, about talking about humidity and filament. So humidity is affecting both PLA in different ways, but PVA and PLA or tough material. Right. It doesn't really. I mean, it's more sensitive in PVA, I suppose, but
absolutely.
Let's talk a little bit about those numbers. What the graphic shows, and why. Yeah, basically describing the graphic.
So this was an early test we did probably, I don't know, 2 years ago, where we had two different drawer bay designs, and we exposed the drawer bay to a relative humidity of 70 and up to 90%, and we were monitoring the moisture and humidity in our drawer bay, and so we have two different horizontal lines here for two different designs, and then also the blue and the orange line showing the humidity of the material over time. or in the drawer bay over time. And
Right.
so here you can just see how the difference of the sealed bay, how well it can perform.
And then here we also have the image on the right showing like kind of the two parts with, I guess that's RH stands for relative humidity.
Mm-hmm.
Okay. So let's talk a little bit of, we've established, okay, the filament will absorb humidity or will absorb water from the environment.
Right.
But how does that translate to your part? What does that mean to your part?
Right, and so both for PLA and PVA, in this instance it's PLA, and so
Mhm.
you can see in the model there is an increase in kind of stringiness and kind of blobbiness happening across the print, and so that's just that the moisture has been taken up in the PLA, and when you extrude and you heat up the plastic, that moisture will evaporate because you're over the boiling temperature of water.
Yeah.
And so what happens is as the material comes out of the nozzle, it won't do what you want. It might pop, it may expand in a way that you don't want because the pressures are changing in the hot end over time.
And we've seen a lot of examples like people trying to fix that problem. At least I've seen them in different 3D printing blocks and whatnot.
Mhm.
But it's not as easy, right? It's not just putting it in a container and that's it, but making sure that the container is sealed. And then also, I understand. So we're doing with method, tracking the humidity at all times.
Mhm.
So it's not just a passive kind of sealed container, but
Mhm.
also being able to track it.
Right. So we have in method when you in our spool we have a piece of desiccant which is absorbing moisture.
Mhm.
And so when you put the spool into the drawer and seal it, you've now controlled the environment, and we actually have a sensor in the drawer that is reading the humidity and the temperature, just to kind of give us some more information on what's happening. Because you could lower the temperature of your extrusion to get rid of stringiness. There's a lot
Mhm.
of things you can do, but then that changes performance elsewhere. And so this is
Right.
just one more control we have to ensure our success.
And then specifically, moving back into the tests or the benchmark test. So what we chose for this one was, if we move to the next slide over, is this gripper assembly. As we talked about it. One of our designers here is Andrew Askedal designed it. It's a pretty nice and nifty little device, right? It's kind of like an end effector, he called it. Basically, it's a complex part, right? It's a print-in-place assembly.
Absolutely.
And as we said before, it has some sort of looser tolerances than what we showed with the cube. The challenge here is being able to use both materials, PVA and PLA, and once they are dissolved. So this is the way. I don't know if you want to zoom in to the part right here. So this is how the part comes out in method, right? All of the clear material is what Michael was describing in his PVA supports. We'll dunk it in water. And after, I would say, in this one specifically, after about 6 to 8 hours, all of the PVA will have dissolved, and you'll have a moving part. So let me bring over the moving part that opens and closes. It's a fairly straightforward mechanism. However, if we go back to the slides, right, and the next slide over, you'll see that's basically me trying to play with, on the right hand side, the method gripper. And on the left-hand side, we have competitors' print. So and we have it here. It's broken, so I cannot do the demo again because it sort of exploded in my hand. And there's two reasons for that, right? It's well, first of all, we knew that there were some over extrusions from that machine, which caused specifically some of the gears to fuse together. But then also we saw, and now it's gone, but the PVA was rather noisy, right? And I think that. What are some of the causes for PVA to become kind of to not behave properly or to be hard to print?
So when the PVA will come out of the nozzle,
Mhm.
it'll be much more apparent that it's absorbed moisture. It'll pop. It'll have bubble or voids, even in the print.
Mm-hmm.
And so a lot of times, what happens, you get a lot of sparse fills in the model or in the support region, and the layers don't adhere properly.
Yeah.
And so then you're not building your surface as well that you're gonna print then your model on top of, and that becomes very hard.
Right, and it's interesting also, like for me at least, even though kind of I was under the impression at the beginning, like, PVA, well, once it dissolves, it will go away, so any defects in the PVA might not be as relevant for your part because it's going away.
Sure.
But
Sure.
it does affect the actual part, the material itself.
It does. If you're building like a floor or something,
Mm-hmm.
and the
So
floor
what do we,
surface
like-
is bubbly.
If we were to say, here you go. But I like just explaining what we mean by the floors and then the supports.
So you have a simple part here,
Uh-huh.
and this is the base.
Right.
You're gonna build PVA to support your model.
Mm-hmm.
And so this surface is really important to be flat.
Right.
And essentially, if it's not flat, you'll kind of get these bumpy surfaces, or there might not be a void.
Mm-hmm.
And so when you then go to print your model, that bottom surface won't come out well.
Right. And then, so that, it's kind of like the ghosting of the surface that will end up affecting that top
Correct.
part, right?
Your interface layer is very important
Mm-hmm.
when you're building your model.
Right.
Some questions.
yeah.
When dissolving the PVA in water, does that affect the PLA at all? Will the part soak up water?
Well, I can tell you, like, my experience with it, but I'll let you, like, go with it.
The part soaks up water in the sense
Mhm.
that we're usually printing at 10% infill, and so what'll happen there is you'll get water soaked into the part, and then you have to maybe drain it out a little bit,
Mm-hmm.
especially for big components that take a lot of infill.
Yeah.
But as far as like, dimensionally, the parts we dissolve and then measure to meet our tolerances, and they still match it. So they're not changing unless you overheat the water for some reason. The part works.
And how long does it usually take to soak?
It depends a lot on the part.
Mhm.
I would say, like, I mean, we have a few examples here, as I was saying. We have the gripper here, and we have the goggles. Both of these, actually, the goggles are a little bit faster because they're less intricate. This one will take about, I would say, 6 hours maybe. This one is a little bit more like maybe an overnight soaking it in water. So if I leave it, once I leave the office and then I come back to a fully dissolved part. It also changes a lot as you use up the water, let's say, because the water itself will absorb some of the PVA, and then there's less water available for you to dissolve the PVA with. Yeah.
How long did the claw take to print?
I think it was a 12 or 16-hour print. Let me check that and then come back to you.
And
But
then they also were wondering if you can print the claw design without supports.
well, yes, you could print it, but then the thing is, so the reason we chose this geometry to test it out, the PVA supports, is because if you were to print it without supports, first the parts would just fuse together. Whenever you have an overhang, kind of like what Michael was showing off here, you'll end up having. So if let's say that, instead of having, I don't have an eraser here, but instead of having this overhang be able to stand out like it is, what'll happen is all of these filaments won't have a place to go, and it'll start drooping. So you'll end up seeing like kind of like this spaghetti effect on the part because it doesn't have a place to rest. If you were to use a single material, and let's say if you printed it on a Rep Plus, which is a single extruder material, you could print it and you could print it with supports, but then you won't have the possibility to remove those supports because of the fact that the part is fairly intricate, right? And it's going to be hard for you to ply them out since, well, these overhangs and these components are
This feature here, in particular.
right, that
The pin.
one, and then everything that's happening in here, right? So getting those supports out with a single extruder, it's going to be tricky. It's possible to print it, definitely, but not for it to work, I would say.
Correct.
Mhm.
Correct.
And then before we move on, a
Yep.
lot of people are asking, does Method support third-party filaments? Can we get the same quality with third-party filaments?
Right.
Will there be an experimental extruder?
Okay, so 3 questions there. The first answer is yes. We don't support it. We offer an auxiliary port, and what I mean by that, there's a port on the side of the machine where you can load third-party materials. We don't advise for that because of the second question, right? You're asking if a third-party material is going to perform the same as our materials. So in a way, we cannot guarantee that. It's for 2 reasons. First of all, well, we don't know what material it is, so we haven't tested it as much, so we haven't validated that it works. And second of all is that if you're side loading it from the machine, it's not only the fact that you're using an unknown material, but it's also not being kind of enclosed as we are enclosing our materials inside of the machine, right? So you're risking, again, going back to Michael's point, you're risking excessive amount of humidity, you're risking basically an uncontrolled material. So we don't know what the results might be. That's why it's possible to print with them. We don't recommend it, but it's there if you want to try it. And then the experimental extruder, that's a follow-up question, I guess. That's, we'll see. So Going back to the deck now, and kind of doing a quick close up on those parts, you see the two grippers here. The competitor on the left, the method on the right, and it seems straightforward. It seems like it's practically the same part, and they seem clean enough. But when you zoom in, and this is what this image is going to be showing, you see, those are the main gears, and you see on the image on the left how they completely fuse together, right? And to be fair, that's a tight tolerance, so it's not easy to achieve that for any machine. And in this case, Method is actually able to do it, fairly well. The parts are actually independent from one another. But I think, how could we explain, and I would defer them to you, Michael, that fusing together of the parts on the left, is that related kind of to the bulging?
Yeah, I'd say it's definitely related to the bulging kind of what we were talking about earlier. And so, you talked about constant extrusion in straight lines, probably has the same diameter of your bead width that you'd expect, but as you move in and out of corners and accelerate and decelerate, keeping that bead width the same is difficult to do.
Right. And that ties back also like with one of the features on the machine, right, which is being able to control the flow of the filament, because it's not only knowing where the nozzle is, but knowing how much material is coming out of the nozzle at any point in time, right?
Right, absolutely.
How do you do that with Method? I mean, how do you control the amount of material that's flowing in the machine?
That's a good question. We run a lot of test prints to determine what our bead width is, and we have certain controls of our filament at certain times, whether we're accelerating and decelerating, making long constant extrusions, to ensure that our bead width is as expected. And there's stuff happening on the back end to control how we're driving the filament to do that.
Okay.
And our temperatures are very controlled.
Yeah.
We have a heated chamber allows for very good dimensional accuracy because the material coming out of the nozzle is in a controlled environment, and your part isn't shrinking and warping.
Yeah, I think, and we'll touch on those two in a second. And then, just to finish up with this section, the next slide over shows these. In this case, it is different parts. But the reason why I wanted to bring that up is because you can see some of this stringiness happening in the PVA, right? This is a different part altogether, so it's not kind of like apples to apples comparison, but still you can see how straight those PVA lines are in Method versus in this case a competitor. And then in the next slide over, just so that we know what we're talking about when we say proper layer alignment and resolution. So that's a different print of the goggles. In that case, the goggles are printed vertically, and there's my finger. So you can see the comparison here. The point here is kind of how do we compare up against your fingertips, right? So if you go ahead and looked at your fingerprints, that's the type of layer lines that we're trying to find and to align. And you can see, the straight lines are like crazy straight. It's kind of, I was impressed by it. And in this case, all of that, curves are basically coming from the shape, but it's also really interesting to see how smooth the transition is between each of the layers, even in such a complex and organic part. In this case, a fillet that's inside of a curve. So it's kind of like curving in 3 dimensions, I would say. Moving on to the next set of features, right? And we started talking a little bit about it, kind of the material flow and the extruders. So we did also create new extruders for the machine. They're much more complex. How would you describe in a nutshell what these extruders do better that we didn't used to do before?
In terms of just better, we have a longer liquefier. So that's the hot component that you're melting the plastic. And so that allows us to push the filament with ease and get higher flow rates. And the second thing is the driving force we have of the traction method. How you grip the filament allows us to push a lot harder with this system.
Okay.
And so that allows for the speeds we're able to achieve. And then we also have a geared system which allows us to maybe get a little more fidelity out of the motor and use a smaller motor at that.
Okay. And then the second feature would be, the circulating heated chamber, and you touched on it a little bit, because we do know that there's a lot of printers that have, heated build plates, and that's something that's definitely, a lot of you guys have been asking, MakerBot in the past, like, why don't we use a heated build plate? So why did we choose to use a heated chamber instead of a heated build plate in Method?
Right. So the heated build plate is really only directly controlling one portion of the print, and let's say the raft portion or something at the contact surfaces and a little bit further up. But as you print larger parts and bigger parts, you're actually moving further away from where you care about, which is the build plane, which is where the nozzles are at.
Right.
And so, really to control the environment in that area is what we're trying to do, and that allows us to keep the part from shrinking and warping across the entire print and not just at the base.
And that's one thing that I know that thermoplastics is a thing, they contract with temperature, right? But how much would you say is it possible to see PLA to change dimension once it cools off if you're not controlling it appropriately? Maybe percentage wise, or is it high?
It's probably, I can't say exactly. I don't know. I can't really remember, but it's probably in like the 1% to 2% or something like that. I think before, when I print in the open air, I maybe scale my part up somewhere less than 2%.
Okay, right. But in a tight tolerance part, then that can mean the difference between it fitting and not fitting.
Correct.
Yeah.
How high of a temperature can the heated chamber go?
So I'll let you answer that one.
This chamber goes up to 55 C. And for our tough material and PLA, we print at 40 C.
Right. Yep. And then it's also interesting to me, like every time that I take the part out of the machine itself, the build plate itself is warm, right? Even though it's not actively warm, it's just soaking some of the heat in the chamber.
Absolutely.
So that's also helping with keeping the part adhered to the build plate and
I think so. It's part of the environment.
So for that one specifically, going back to the slides, we chose this. It's also, again, we tried to make it, well, in the case of the gripper, it's not that simple of a part, but the rest of them are like straightforward tests that anybody can understand. In this case, this hub, right? And all there is we are trying to fit a predefined external geometry, so one that's not printed. So how does this part play and the printer play with external components? In this case, it's bearing, and just trying to fit it into a tight hole, right? And then what we did is basically printed both parts or both STLs in the same machine, and we touched on it briefly at the beginning of the conversation, right? Where, well, what would be the main reasons why we see a nice smooth circle that actually I have to press the bearing for it to fit, but it's kind of like
as intended,
as intended, right? It's a press fit, so it's going to be attached to the outer component and then be able to spin. But on the other part, and just don't move the simulator to make it match. Here we go. Right in the other part, in the desktop print, it's not being able to slide in, and we measured it, right? So if we take two axes, it doesn't really matter which one. It's not the same. It's kind of like an oval shape instead of a circular one. What would be the reasons behind those changes?
I think the first thing that comes down to it being an oval is probably in the gantry and the system as far as trying to make a circle. If you think of them as just the 2D layers, it's going to be repeatedly making a non-circle over and over again, and that just comes from either kind of the warp in the system or how it's deflecting in the frame, or slop in the belts and pulleys potentially. And the second thing would be just the overall size being undersized, overall part being undersized, which is the heated chamber. And so that allows the part to not cool at unexpected rates and to keep our dimensional accuracy.
So it's possible that some of the beginning layers are going to be perfectly aligned in the desktop printer because of the fact that they're benefiting still from that heated build plate. But as you scale up or as you go up, then it's going to start affecting that top circles.
Yeah, it'd be interesting to measure the part at the bottom of the circle and at the top of the circle, and you might be able to see the difference there.
Right.
And as it changes.
And just as a reference, because I was measuring this with the calipers, we we heard a lot of conversations in Twitter, and we love your guys' comment, and people asking, hey, did you cool off the bearings? Did you do anything to the parts? So it's not, and it's just the fact that in the method part, the difference that I saw, I think it was about 20 microns at most when measuring it in two directions. And then on the desktop printer, the difference was around 120, 150. It doesn't sound like a lot, but I mean, that's something that you have to accommodate if you're using more maybe basic system, but just giving yourself a little bit more room to play with.
And I'm sure if you made the part bigger
Mhm.
by that 150 microns, the
Mhm.
bearing would fit, but then it wouldn't have that interference fit you want, and the part would move
Right.
around and wobble.
Right, and that's a tricky part, right? Because then you start. I mean, it's possible to solve for it, but then
Mhm.
you sort of have to play with your model in CAD and try to figure out
Right.
what's failing and
Right.
compensate for that. So
If you did any lifetime testing, it'd probably affect the performance of the bearing,
Mhm.
that it doesn't have a nice compression all the way around,
Right. Right.
things like that.
And then another kind of example of the accuracy is kind of this part we printed as it's a mouse. I don't think I do have it here. I won't spend too much time on it, but it's kind of like going back to how do we sum it all up. In this case, it's a mouse assembly. So you can see top left corner. It's kind of like the battery lead. On the right hand side, it's the top view of the body, and everything is printed in a single go, which means we printed all of the components for the mouse at once. And it's really tricky because one thing is to create supports for your part, but once you're trying to create supports for a part that's going to be printed on another part,
Mm-hmm.
it becomes kind of a little bit more of a challenge with PVA, right?
Right.
Why is that? So I mean, the tricky part is to connect PVA, like the change in materials every time, or
Yeah, so the parts want to shrink and contract,
Mhm.
and so you're not just laying your model material on top. You're actually adhering them together,
Mhm.
and the support just as much to put your material on is actually to anchor it down and to keep it in place. So your adhesion is really important, and so
Right.
if you don't control the environment very well
Mhm.
with like a heated chamber, your parts don't adhere well, and they
Mhm.
cool, and they start to delaminate from each other,
Right.
and then you won't have your part accuracy.
So it's interesting that you say that because then in a way it's not only controlling the parts delaminating against the plate itself,
Mm-hmm.
but in every single layer, which is something that we've seen, right? It's
Correct.
possible for parts to delaminate in a layer further up.
Right. I think I used to print some on a 2x, some blocks,
Mhm.
and the bottom of the print would be very nice, but as you get higher up, the part actually starts to warp and contract, and it
Mhm.
cracks the part.
Yeah, yeah, it's a lot of tension between the filament and the
Absolutely.
environment. So next up we have like kind of like that GIF again explaining what we just saw with the bearing, and again it's just it's an easy test and there's ways to circumvent that. But the point here is we're using the same part. We're trying to create something that allows an engineering like yourself, a designer like myself, to be able to trust the machine
Right.
and say, hey, this needs to be 80 millimeters. What's the tolerances that I need? How is it going to perform? Trusting the fact that if I design something in SolidWorks in Rhino,
Mm-hmm.
it's going to come out the way that I want to, and not
Yeah. Not having to struggle with 3D printing is
Right.
really what this allows for.
right. And I think that in that regard, I think you also brought some of the parts that you use for the injection molded parts that you
Mhm.
use for the machine. Yeah, if you want to talk
Yeah,
briefly
so-
about it, because that's something that you were not able to do before we had Method in house, right? Or we're having a fire simulator. So how's it called?
Fire drill?
Fire drill, right? So we'll just wait for that to go away. But we're talking about, how does this part match, between the injection molded part and the printed part with Method? So these are actually housings that you created for.
Yeah, these are the. Just go ahead.
We'll just wait for a second.
Okay.
They're just letting us know that they're doing a fire drill test or something. It's always when we have it like once a week or so.
Yeah, probably once a week,
Yeah,
sometimes more.
yeah. So there we go. All right.
All right, so what I have here are a mix-up of extruder parts that we've designed on Sombrero. So on the left, I have the extruder housings, which is a PPS material, nylon glass fill.
Mm-hmm.
And then I have the gearbox printed, which is a pretty complex part.
Nope.
Comes apart.
Love some of the gears. That's okay. You can keep on.
And so here I'm able to print the part on the Method, dissolve the PVA,
Mm-hmm.
and prints as designed. I can put my pins in the parts, which are about 3 millimeter size pins, and all my parts mesh together very well, and even in the injection molded parts. And so I'm able to swap the components and not have any sort of fit issues. No post processing. I was able to stick a bearing in here and tap the threads
Mhm.
or use thread formers, and all the fits are more or less the exactly as I expect between the injection molded and the print, which is really nice.
And that's interesting because we were talking about it yesterday. Specifically the fact that you were able to be going once you had the machine to be able to test out kind of the press fit tolerances that you wanted
Mhm.
from the injection molded part before you had to commit to the mold itself, which is kind of an expensive mistake if you make one.
It can be in terms of like time and having to make the change.
Mm-hmm.
It can be of a nuisance, or if your performance isn't as you expect out of the part, you might not know, is it a design problem
Mhm.
or is it a part problem, a
Yeah.
quality problem.
Yeah. And then kind of moving on back into our deck. So it's not only the fact that we've seen this happen once or twice, right? But we are testing these printers for quite a few hours, right? In this case,
Right.
like what are we now? Over 200,000 hours of testing.
I think so. It's gotta be up there if I. Yeah,
Right.
I think though.
And how's that going? Like, do you have like a multitude of machines just running 24/7, or?
Yeah, so we have technically two different batches of machines running, an older model or earlier in our testing process, which has I think over 3,000 hours per machine, and there's probably 40 of those running, and then we have another group of 80
Yeah.
which we've tweaked our molds or improved our assembly process,
Mhm.
and those 80 have been running for an extensive period of time as
Yeah,
well.
That's crazy.
And
So
that-
yeah. No, go ahead.
Those are just run in kind of a controlled environment where
Mhm.
we run our test sprints over and over again to
Mhm.
find either lifetime failures or kind of faults in the machine that we can improve.
Right, and that's also part of the whole conversation about having a professional grade printer, which is something that you want to trust, right? You don't
Mhm.
want to find out halfway through the life cycle that it's just not performing as expected. So,
Right.
and then in a nutshell, I would say, going back to the next slide over that overall, the way that I look at it, what we're trying to do with Method is control four big items: the materials,
Mm-hmm.
the environment, the print environment, the being able to offer it, as an accessible product, so something that I'm able to just walk to and start a print, have it around in the office, not have it gated somewhere in the machine shop. And then the fourth bit being, having an accessible total cost of ownership. And we've heard a lot of comments, in Twitter and Instagram about, how cheap can we say that a $6,500 material printer is. The thing is, when you compare it to an actual desktop system that is going to be performing at the same level, you're talking at an entry price of $20,000 plus dollars, right? So
Sure.
that's what we mean by the lower cost of ownership, right? So when comparing apples to apples, when comparing the features that we're able to support with the machine, with the features that as such a machine delivers and the price point of those, then that's when we say like it's actually breaking something, in that continuum of prices in the printers. And overall, as we said, you guys might know this, we've talked about the method at length, but we have three big ones, and I'm going to introduce a new printer because we'll be doing the next webinar on that one. So we have now the Replicator Plus, the Method, and the C18. Overall, I would say that the Method and the C18 are the better suited for professionals just because of the qualities that they offer. C18 is still a single extruder machine. But the cool thing about that, and I'm just bringing this up because of the fact that we'll do a next webinar probably on the C18, but it's kind of like, that's where you're able to print things like these, right? So this is a robot arm that I printed late last year. It's kind of cool, right? It's an assembly, of course, but it has a lot of different joints. We took this, we got this model from our friends at Kuka. But being able to print massive parts for a professional is also really important. And by the way, this is kind of my segue to saying that right now, out of the professional offering, specifically the C18 offering, we're running a promo on it. It's $1,000, I think. So yeah, just FYI, it's
$1,000 off.
$1,000 off. It's a pretty nifty machine, right? But yeah, I think that in that way that rounds it all up, and I'll just open the floor for any questions that you guys might have. Alison, if you want to
Yeah,
let us know.
got some questions. For Method, in the future, is it possible to use other materials like ABS?
Uh, so let's say that we're working on a roadmap of materials. I cannot comment specifically on which ones will be coming first, but we are, as Michael mentioned, like we now have the ability to have a heated chamber. Many people know what that means for materials. We have a higher range of temperatures that we can achieve. So we're working on a full range of materials that will be coming up as we develop the machine. The first ones right now are PBA, PLA, Tough, and PETG. I think it's almost out the door, but we have a few more in line to be offered.
Let's see. I don't have a lot of success printing unless I use a full raft, but it can be such a waste of material. Is the method better at printing without a raft with a good quality floor layer?
So the raft is a tricky one. I think that for me, and actually, I have a good example here with the part with the raft. You don't need to submit it, but it's actually, it's the same goggles, but it did print with the raft and the method. The reason why I like the raft quite a bit, so I'm just able to peel it off, is because it does give you, the confidence that you're starting in a zero layer. There is going to be some waste associated to it, that's for sure. But I would rather have a little bit of extra material on the part than compromising the part itself, which is kind of like way more material to be wasted if it fails, right? So it's like, I would describe that raft as that kind of like your zero layer that makes sure that everything is running.
Absolutely.
Yeah.
Do you need to redo the offset calibration if you change the nozzle?
Do you need? Right, and it's actually an automated process. I wouldn't recommend changing the nozzles in this one because these extruders are not, unlike the experimental extruders.
You change the extruder though.
Oh,
Yes. Every time you change the extruders, you'll have to recalibrate, and it's an automated process, which is really nice on this machine.
yeah.
And so that auto calibrates in X, Y, and Z.
And actually, I'll just show you guys for a second. Like, if we move over to the webcam over here, it's not running. Oh, it died. Okay.
Yeah.
I was gonna show you like the place for the machine to actually measure itself up because that calibration is automatic. So the machine, once you change the extruders, will allow you to just do the calibration on its own. And unlike other machines where you actually have to print something and then measure it up against a grid, a reference grid, in this case the machine just does it automatically. It's kind of nice too. So, yeah.
Will the method accept the same file format as the other previous MakerBot printers?
Yes, and that's actually not, it's not on the method itself, but on our software, MakerBot Print. We haven't talked a lot about it, but we've iterated on it. So right now we're supporting, I think, over 25 native CAD file types. So a OBJ, STL, SolidWorks, SolidWorks parts, SolidWorks assembly. There's a myriad of them. STEP that you can just import directly to the interface on MakerBot Print. Like, if you guys are curious about that, we could do like a short webinar on it. But definitely, so it's all of the files that we have supported in the Rep Plus and in the C18, but now with the ability to print with soluble support, which is kind of like the big step forward.
Somebody was asking about the KUKA arm. They said there's no way that could be printed on a Z18.
What? Yeah,
Can you explain how?
Oh, I see.
Because
Okay.
that cannot fit dimensions.
Right. Okay. So that's what I meant when I said, it is an assembly. I don't want to break it apart, but you can see. Let's see. So you can see every component specifically for it to be to rotate freely. So each of these, I think it's 8 components. So let's see, 1, 2, 3, 4, 5, 6, 7 components. It's printed individually. The C18 though offers 45 centimeters. So for that, that's kind of how many inches?
12 by 12 by 18.
18 inches, right? Well, C18, of course. So that would be, if you wanted to print it in a single go, what you'd achieve with it would be about yay big, so about half the size. However, you could also print it like all folded up. We did an interesting test with the method on it, like how do you challenge the print volume by printing something that folds and then disassemble. So we can show you that at a later time. But yeah, this KUKA arm wasn't printed on a single go because since the C18 doesn't have soluble supports, I needed to have it, individual pieces printed each time. So it's 7 parts, fairly big one So the maximum size is about 18 inches. I don't have a specific print right now with me that shows off that height, but it's pretty big. Yeah.
Cool. I have a MakerBot Z18. How does Method compare in print quality to the Z18?
I'd say it's much better.
Mhm.
It's pretty night and day what the method does against our existing printers. So
Yeah, and I think that it's also like the interesting thing here is that the slicer team, and slicer team is the guys that work, guys and girls that work on creating the tool path, basically the instructions for the machines to describe the shape. They're improving not only the method tool pathing but also the rest of the lineup. So we've seen a lot of improvement kind of derived from method and following into our existing lineup. The biggest difference is on one hand, Z18 prints massive, and on the other hand, it only uses one filament, right? So you have to use breakaway supports, not dissolvables. And method, well, it's the dissolvable supports is higher level of accuracy and complexity of the parts for that.
What is the expected lifetime in hours for extruder? For the
For
method extruder?
I'm not sure.
I'm not sure we have an exact number on that.
I would have to defer to the website maybe on the tech specs. I don't have them on the top of my head, but it's quite a few. I think that I've run at least this extruder for a good couple thousand hours and they're running smoothly. I'm not sure the exact number, but I would defer to the tech specs. Or if you want to, send us an email, and I know that somewhere in there should be like hello@MakerBot in case you have like more follow-up questions, and we'll be happy to address those.
What changes are coming to the print software? Will it be faster
Right.
for
So.
slicing?
Right, and actually, we are running right now a series of beta tests for the print software. I have it myself, and it's considerably improving, especially because of the fact that right now, since you have two materials, it's kind of a much more complex set of geometries that you have to evaluate. It takes a little bit longer at the beginning, but now it's improving. So I don't know when it's slated to go live. I believe it's by the end of March or mid-March, but it should be coming up shortly. And yeah, it's definitely faster than what it used to be. Okay. Is there any other questions? Oh, there's a lot of questions. That's good. No.
Yeah. Is there a plan to launch a bigger printer with the same setup?
So I cannot say anything specific, but what I will say is that we developed, and you can touch on that as well, Michael. But we developed Method not as a single printer, but as a platform,
A
right?
platform and architecture to go forward with in the future, and I think that's what it offers.
Yeah.
So-
So, we kept the door open for that. I'm not saying when or what it is, but definitely something that's now possible with this architecture.
Very specific. What type of encoder is used to detect a jam?
What type of encoder is it?
So on this system, we have a Hall effect sensor, and it's uses a diametric magnet to track the revolutions of our encoder wheel and how the filament's moving or not.
Mhm.
I have an interesting question. Why did you choose to have a high accuracy printer with specific materials available? How does this compare to high requirement applications that also need more engineering materials?
Why did we choose to do it? Well, I think that we saw that there was a gap in the market between the two worlds, the desktop ones and then the professional industrial setups. I think that that's kind of the niche that we found and we wanted to develop on. So yeah, I think that we all know that MakerBot has been really successful in the EDU sphere now with the Replicator Plus being all over the place. But I think that was the main reason, right? Being able to find an opportunity in offering something that would deliver the qualities and the type of machine that a professional wanted to. We saw that nobody really was delivering on that. And of course, the fact that we had access, we started developing this machine back when we first started our partnership with Stratasys, right? So having access to that high level IP is really interesting because we were able to sort of bring the price down and offer it, at a more accessible price range.
One last question that I see here is third-party slicers. Are we going to be able to open it up to third-party slicers?
I'm not sure if that's on the software team's roadmap. I would say, not at the moment. The reason being, well, just because we are kind of, as we said, working with very specific tool pathing patterns. So as Michael was describing, it's not only the fact that you're able to do a corner, but understanding how the printer is going to behave in a corner, how is it going to accelerate in and out. So in a way, it's offering kind of like consistent quality, what we're trying to go for, right? And then, also I would say that it's important to know that the software that we offer is entirely free, so anybody can download it. But yeah, the answer for that one is no, not at the moment. So I think that with that, it's been really good to have you guys. It's always exciting time for us here doing a webinar. I hope that you guys enjoyed it. Thanks a lot, Michael.
Absolutely.
It's been really good. And let us know if you got any questions. As I said before, shoot us an email at hello@makerbot.com. We'll be more than happy to answer them. And remember the C18 promo. I think that's pretty cool. I love that machine myself, specifically for big parts. But yeah, probably the next webinar will be on that, and then we'll talk more on what are the parts that you can print with it, what are we seeing people, and we'll probably bring some more guests here to talk about their experience with the C18. But for now, just keep in mind it's $1,000. That's quite a bit. But yeah, thanks for watching, and then we'll see you next time. So thank you.
Bye.